Hello, my name is Chung, a PhD candidate at IIIXR Lab. Today, I will introduce a paper, GSGEN, Text to 3D Generation using Gaussian Splatting, which was presented at CVPR 2024. GSGEN aims to automatically generate a 3D scene that matches the input text provided by the user. This task is referred to as Text to 3D Generation. Recently, there's been a lot of exciting progress in the field with the use of NERF technology and diffusion models, making it a promising and active area of research. The core contribution of GSGEN is its replacement of NERF with a technique called 3D Gaussian Splatting, achieving substantial performance improvements in various aspects. And this presentation will start by explaining 3D Gaussian splatting to make the core contribution easier to understand. It will not cover the basics of NERF and diffusion models from previous research. First, I will explain 3D Gaussian splatting, referred to as a potential game changer of 3D representation. Original 3D Gaussian splatting aims to reconstruct a 3D scene from given multi-view images to synthesize novel views that were not initially provided. To achieve this, it defines a novel 3D representation like meshes, voxels, and point clouds, and includes efficient method for rendering the representation. When it comes to previous research on Earth, given multi-view images, the method reconstructs 3D scene by representing the geometry and regions of the scene using a neural network. This implicit representation is differentiable and compact, making it easy to train and capable of generating high-quality 3D scenes. However, the process involves sampling and calling the neural network for each sample, which results a very high computational load. Consequently, both the training time for 3D scene reconstruction and the rendering time for the learned scene are quite long. In contrast, 3D Gaussian splatting introduces a new paradigm by utilizing learnable 3D Gaussians as an efficient 3D representation. These Gaussians are optimized under the supervision of multi-view images to accurately represent the scene. Because it's an explicit representation, it can be stored as a data structure while maintaining the implicit characteristics of a continuous function. Additionally, by developing a GPU-friendly rendering process, 3D Gaussian splitting achieves remarkable performance, including high-quality results, fast training, and real-time rendering. 3D Gaussian splitting can be divided into 6 stages. First, a 3D point cloud is generated. This point cloud can be created through random sampling or based on feature points inferred from multi-view images. In the original paper of 3D Gaussian splitting, the point cloud is initialized using the structure from motion (SFM) algorithm, which reconstructs 3D structures from 2D image sequences. Second, a 3D Gaussian is assigned to each point. From a geometric perspective, a 3D Gaussian is identical to an ellipsoid, which helps fill the empty space in a sparse point cloud. This leads to much higher quality rendering results compared to traditional point-based 3D representation. A 3D Gaussian is defined by its mean and covariance. In practice, it's represented as an ellipsoid where the mean denotes the center point and the covariance is expressed as the product of a scaling and the rotation matrix. The parameters of the 3D Gaussians are subject to optimization, and additionally, each point is assigned a color and opacity, which are also optimized. Next, the 3D Gaussians are projected into 2D Gaussians and transformed into pixel space through a GPU-friendly rendering process, a fast differentiable rasterizer. The key to this fast differentiable rasterizer is a tile-based approach. It defines tiles as 16 by 16 pixels and allocated a thread block to each tile. This design increases the utilization of shared memory, thereby enhancing rendering efficiency. The final color of pixel is calculated using point-based alpha blending. Given a pixel's position, alpha compositing is performed for all overlapping Gaussians along the camera ray. As shown in the equation below, the final opacity is calculated based on the mean and covariance of the projected 2D Gaussians for each point. This final opacity value is then used as the alpha value, which is used for blending the color values calculated by spherical harmonics to yield the final color of the pixel. This complete this completes the forward process, and then to accurately represent the 3D scene corresponding to the given multi-view images, the parameters of the 3D scenes need to be optimized. For this, the loss between the multi-view rendered images of the 3D Gaussians and the ground truth images from each corresponding view is calculated. This loss is then used in backpropagation to perform the optimization. The loss is defined as the sum of the L1 loss and the DSSIM loss between the two images. In the optimization process, another crucial stage is adaptive density control. Initially, when the point cloud and 3D Gaussians are generated, they are based on a sparse point cloud. Therefore, at certain iterations during the optimization, the density of the 3D Gaussian must be adjusted. This involves removing 3D Gaussians that are nearly transparent due to very low opacity, and duplicating 3D Gaussians in empty spaces, or splitting 3D Gaussians with a very large covariance to adjust the density. Basically, every 100 iterations, it is determined whether to perform density control based on the view space positional gradients, which are the average gradients of the positions from the view. This process is crucial as it significantly affects the final quality of the 3D Gaussian splitting results. After the optimization is complete, the 3D Gaussians, which represent the geometry and radiance of the 3D scene, reconstructed from the multi-view images, can be stored. This allows for the rendering of images from novel views that were not previously seen. The values of the 3D Gaussians can be stored as a data structure, enabling real-time rendering performance through GPU-optimized rendering. Looking at the overall process, 3D Gaussian splitting is a learnable 3D representation similar to NURBS, but it demonstrates superior performance in terms of training and rendering speed. Even in terms of result quality, it is outstanding. Therefore, by modifying certain stages in the 3D Gaussian splitting process, we can achieve text to 3D generation while retaining all the advantages of 3D Gaussian splatting, similar to how nerve evolved to perform text to 3D generation tasks. GSGEN proposes new approaches in three stages. First, point cloud initialization. Second, optimization. And third, adaptive density control to generate 3D scenes from text prompts instead of multi-view images. First is the point cloud initialization stage. Unlike the original 3D Gaussian splatting, which generates a sparse point cloud from multi-view images using the SFM algorithm, GSGEN needs to generate a point cloud representing the 3D scene implied by the text prompt. While random sampling could be used to create a point cloud, it might lead to degenerated 3D objects, depending on the quality of the initial point cloud. Therefore, it is crucial to have a method that can convert the user's text prompt into a 3D geometry. To achieve this, GSGEN employs a diffusion model called point E, which performs text-to-point cloud generation. Point E can generate a point cloud and color that accurately represent the 3D scene described by text. The generated output serves as the initial point cloud and color values for 3D Gaussian splatting. Next is the optimization stage. Just as we replaced multi-view images with text prompts earlier, we need to develop the optimization process so that the rendered images of 3D Gaussians can be guided by text prompts instead of multi-view images. Original 3D Gaussian splatting could use image domain loss because it compared two images. However, GSGEN must compare the image rendered from 3D Gaussian splatting with a text prompt. Therefore, to guide the alignment between image and text, which are two different modalities, we use the stable diffusion model. It has been proven in the text-to-3D generation field that stable diffusion is highly effective in inducing alignment between text and image. Typically, the score distillation sampling (SDS loss) is used as a diffusion prior. However, when using stable diffusion, which takes 2D image as input, a genus problem arises. This issue occurs because during the process of aligning multi-view images with the text, the images rendered from different views overfit to the text individually. As a result, when reconstructed in 3D, the scene appears with multiple faces. In other words, using a multi-view 2D prior leads to inconsistencies between views, resulting in a 3D geometry that has a similar appearance across different views. To address this, GSGEN utilizes point E, which was initially used for point cloud initialization, as a 3D diffusion prior. Unlike the 2D diffusion model, point E has learned the alignment between text and 3D point clouds, reducing the genus problem and encouraging more consistent 3D generation. So in summary, to guide the alignment between the given text and the 3D Gaussians, we use stable diffusion as the 2D diffusion prior and point E as the 3D diffusion prior. This approach is mathematically formulated as the sum of 2D SDS loss and 3D SDS loss, and the final loss function optimizes the 3D Gaussians. In the paper, this stage is referred to as the geometry optimization stage. The last is the adaptive density control stage. Since we have modified the loss function and added the 3D prior according to the given text input, we cannot maintain the same approach for density control to adjust the detailed quality of the final output by regulating the density of the Gaussians. In this paper, this stage is referred to as the appearance refinement stage. It employs approaches such as compactness-based densification and penalties to ensure geometry consistency. Since these designs are somewhat handcrafted, I recommend referring to the paper or the GitHub repository for more detailed information. In summary, GSGEN combines 3D Gaussian splatting with diffusion priors to achieve fast training and real-time rendering performance in text-to-3D generation tasks. In the point cloud, uh, in the point cloud initialization stage, it uses point E to generate a point cloud that matches the text prompt, enhancing the fidelity of the initial geometry. In the optimization stage, it ensures 3D consistency by integrating not only the 2D diffusion prior, but also the 3D diffusion prior. In the adaptive density control stage, it enriches texture details through compactness-based densification and penalties to ensure geometry consistency. This approach results in a quality that is reasonable and comparable to state-of-the-art researches. Here are the results of GSGEN based on various text prompts. Next, here are the results comparing GSGEN with state-of-the-art models in terms of quality. Compared to the initial model, Dream Fusion, GSGEN demonstrates superior quality. The outputs are significantly sharper and more detailed. On the other hand, when compared to Magic 3D, we can see that the quality of GSGEN does not fall short. It is same to Fantasia 3D. Thank you for listening to my presentation.